So that's one of the keys to this problem. We're now going to look at this block over here. And what we have is we have M1, and there's two forces here. We have this force pulling this way, and there's an equal and opposite tension over here acting backwards. Remember, if the rope here pulls the same way in both directions, so if there's 45 newtons of pull on this acting this way, there's 45 newtons of pull acting this way. So the sum of the forces on this mass is we have the F acting to the right minus the T acting to the left equals to mass times acceleration. This acceleration that we just solved for is the same acceleration that's over here, and allow us to solve for F. Now, F now is mass times acceleration plus T. So we can go ahead and plug in and solve for what the F is. This mass, this M2 mass, is 322 kilograms times 0.18 meters per second squared plus this 45, T is 45 newtons. So that would mean that the F is, let's get out our calculator, 322 times 0.18 plus 45, and I get about 103 newtons. Or if I round it off, it would really be 100 newtons if I round it off, or 1.0 times 10 to the second. So that would mean that the maximum force, essentially the maximum force that could be pulled is about 100 newtons this way. But this kind of problem, you can see how this kind of problem is quite easily solved. One thing is realizing that both of these boxes move together. So if this accelerates with a certain acceleration, this box moves with a certain acceleration. They all move together. The other thing you can do is you can break it up. You break it, you go to the very last one where there's only a tension on one of them. You write F equal ma, or tension equals mass times acceleration. You can solve for the acceleration. Then you come to the next one, and you say, again, sum of the forces equals 0. There's a force this way that you're pulling with, and then there's tension, the same tension force acting back. And so you can solve for what this force is. One final comment on this, and that's this, is that we can certainly say this. We can say, suppose we wanted to treat these two masses as one combined entity. Could we do that? Absolutely. We could say, I'm going to look at this entire quantity together, and what we have is we have a total mass of M1 plus M2, which is, let's see, 245 plus 322, which is 567 kilogram mass total. Okay, and the total force, the sum of the force is equal mass times acceleration. We could certainly say that again, if you look at the total, in the total picture, there's only one force is being pulled. It's this F force to the right equals the total mass times acceleration. Could we say, let's see if we can plug this in. If the total mass is 567 kilograms, the acceleration I think was 0.18 meters per second squared. If I remember right, that's what it was. If we multiply this out, 567 times 0.18, and we get about the same number, 100 newtons. So, which has to work. So it's just, you can look at these problems in various ways. Of course, if you look at the problem as a whole like this, and you don't know what this is, don't know what the force is, you would not be able to solve for what the acceleration is. So you have to really break the problem up into two problems to really be able to solve for the acceleration. In this case, you can do that because they give you what this tension is. So, hope that's clear. Well, there's a lot of different, it seems like there's a lot of different parts and pieces to this chapter, but actually all of this chapter flows from just simple applications of Newton's second law, F equal ma. And you're using the sum of the forces in the horizontal dimension, sum of the forces in the vertical dimension, or if you're on an inclined plane, it's the sum of the forces along the plane versus sum of the forces perpendicular to the plane. So all of these cases, in all of the cases, all of these equations can be solved for by looking at the sum of the forces and then saying it's equal to a mass times acceleration. So, hope this is clear, and we will talk with you next time.